Hello everyone, and thank you for watching. In this video, I'm excited to present our CVPR 2025 paper, Mask²DiT, Dual Mask-Based Diffusion Transformer for Multi-Scene Long Video Generation. This work focuses on pushing diffusion-based video generation toward longer, controllable, and coherent multi-scene outputs. Let's begin with the motivation behind our work. First, here's a quick look at some of the most popular video generation models to date. As you can see, most of them are still constrained to single-scene videos, with both open and closed source systems typically limited to just 5 to 10 seconds in duration. These limitations can be broken down into three major challenges. Duration limitation: most models struggle to produce long-form video content beyond 10 seconds. Single-shot limitation: they lack support for scene transitions and narrative structure, making it difficult to generate multi-scene videos. Poor coherence: it's also challenging to maintain content consistency over time, especially across scene boundaries. Together, these issues significantly limit the usability of current models in real-world applications beyond short-form entertainment. Our work is driven by three core questions. First, how can we generate longer videos with coherent progression? Second, how can we build multi-scene narratives with controllable structure? And third, how can we ensure temporal consistency and accurate visual textual alignment within each scene? Next, we'll go over related work and why existing solutions are still limited. We categorize related work into three main lines. The first is LLM or agent-based methods, which generate multi-scene scripts using large language models and render each scene independently, for example, Video Studio and Video Directorate. Second, keyframe-based methods such as story diffusion first use text-to-image models to generate keyframes for each scene, and then connect them using pre-trained image-to-video models. However, these approaches often suffer from poor continuity. Lastly, fine-tuning-based methods like TALC improve multi-scene capabilities by adapting the conditional input, but they are often limited by the scalability of the underlying UNet architecture and struggle to maintain visual consistency. Now that we've seen the limitations of existing approaches, let's dive into our proposed method, Mask²DiT, which is specifically designed to support long, controllable, and coherent multi-scene video generation. Before diving into the architecture details, let me first highlight what our model is capable of. Mask²DiT supports two key generation modes. On the left, you see fixed-count multi-scene generation, where the model generates an 18-second video in a single pass, guided by 3 text prompts, each controlling a 6-second scene. On the right, we show auto-regressive scene extension. Here the model is first given 2 scenes, and then generates the third scene as a natural continuation, conditioned on the previous 12 seconds. These two modes together enable both controllability and scalability in multi-scene storytelling. We use cogvidiox as the base model, which follows an DiT-style video diffusion architecture with expert routing. During training, instead of predicting raw noise, we adopt the V-prediction formulation, directly regressing the velocity in the diffusion process using an MSE loss. Building on top of cogvidiox, we introduce a novel pipeline that enables both multi-scene controllability and cross-scene coherence through multi-prompt conditioning. The key innovation lies in 2 types of masks designed for different stages of the generation process. First, we use a symmetric binary attention mask to structure the full attention layer. This mask allows text and visual tokens within the same scene to attend to each other, ensuring semantic alignment, and at the same time, it enables all visual tokens across scenes to attend to one another, which improves visual consistency between scenes. Second, we introduce a segment-level conditional mask, which operates not on attention, but on the input time steps of the visual tokens. Specifically, it sets the diffusion time step to 0 for the first and 1 scenes, meaning these tokens are not noised and treated as context, and sets the time step to t only for the current scene, n, so that only this scene is denoised and contributes to the loss. This allows us to train the model for auto-regressive scene extension, enabling it to generate a new scene conditioned on previously generated scenes. We now take a closer look at the symmetric binary attention mask. As shown at the top, we explored several attention mask variants. V1 is a simple per-scene diagonal mask. V2, which we ultimately adopt, enables full visual token communication across scenes while keeping intra-scene alignment with text. V3, similar to shot adapter, extends the attention mask to allow inter-scene textual token interaction. Among these, V2 offers the best balance between inter-scene coherence and scene-level controllability. However, applying this mask across long concatenated sequences leads to large attention memory footprints. To address this, we introduce a grouped attention mechanism. For every self-attention layer using the mask, we replace it with two n-cross attention operations, where n is the number of scenes. This decomposition significantly reduces memory while still preserving the global attention structure across visual tokens. To effectively train our model, we adopt a two-stage training strategy. In the pre-training stage, we sample 3 single-scene clips from Panda 70 meters and concatenate them, but without enforcing any semantic relationship. The goal here is to help the model adapt to longer token sequences. Then, in the supervised fine-tuning stage, we switch to a curated set of 5,000 cartoon videos, each containing 3 consecutive scenes with contextual relationships, filtered by ViClip to ensure high inter-scene similarity. During fine-tuning, we use a mixed training strategy. With probability p equals 0.5, we perform auto-regressive scene extension. Only the last scene is denoised and contributes to the loss. With probability 1p, we train all scenes in a standard diffusion fashion. This dual-mode setup ensures that the model can handle both fixed-count scene generation and scene-wise expansion. For training, we use a batch size of 8, resolution of 480 multiplied by 720, and a learning rate of 0.00001. This chart shows the captioning prompt we designed for Gemini to generate consistent descriptions across multi-scene cartoon videos. Next, we move on to experiments. We begin our evaluation by introducing the multi-scene test dataset we constructed. This benchmark consists of 50 test samples, each composed of 3 prompts that describe a multi-character scene progression. We used ChatGPT to generate diverse and coherent descriptions based on a predefined structure as illustrated here, where each scene specifies characters, appearances, and a reference caption. This dataset enables fine-grained evaluation of both intra-scene alignment and inter-scene continuity. To assess our model's performance, we adopt the following evaluation metrics. Visual consistency measures the visual coherence between generated scenes. Specifically, we compute the average pairwise similarity across the 3 scenes using ViClip's visual encoder. Semantic consistency evaluates how well each generated scene aligns with its corresponding prompt. This is calculated as the average video-text similarity across the 3 scene prompt pairs. Sequence consistency is defined as the mean of visual and semantic consistency, capturing both visual flow and textual alignment across the full sequence. In addition, we use the Friche video distance (FVD) to assess video quality. We now present the quantitative results of our evaluation. First, we compare Mask²DiT against the strong baseline cogvidiox, using both 2B and 5B model sizes. As shown in the upper table, Mask²DiT outperforms cogvidiox across all consistency metrics, achieving higher visual, semantic, and sequence consistency while also generating more realistic videos, as indicated by the lower FVD scores. Notably, even compared to cogvidiox 5B, our model achieves significantly higher visual consistency, 89.2% versus 43.8%, and better overall sequence consistency with a lower FVD of 607.6. We also benchmark our method against other state-of-the-art multi-scene video generation approaches, including Story Diffusion, Video Studio, and Talc. As shown in the bottom table, Mask²DiT achieves the best visual quality, the strongest sequence consistency, and is the only method that supports auto-regressive scene extension while maintaining high coherence across scenes. These results demonstrate that Mask²DiT not only scales to longer, multi-scene videos but also sets a new standard for controllable and coherent video generation. To further validate our results, we conducted a user study involving human evaluators. As shown in the top table, Mask²DiT is strongly preferred by real users, winning top scores in visual consistency, semantic alignment, video quality, and overall experience. This confirms that our improvements are not only measurable by metrics, but also perceptible and meaningful to users. Next, we present an ablation study on different attention mask variants. We evaluate 5 attention configurations V1 through V5 and visualize both quantitative results as shown in the bottom table and qualitative differences as illustrated as this picture. Among them, V2 strikes the best trade-off. It achieves strong inter-scene visual consistency while still maintaining intra-scene semantic coherence. This justifies our final choice of using V2 as the default attention mask in Mask²DiT. To further analyze our system, we perform 2 ablation studies on 1. The VI-CLIP similarity threshold used in dataset filtering, and 2. The effect of the pre-training phase. On the top, we show results using different interclip similarity thresholds when constructing the fine-tuning dataset. We find that using VI-CLIP filtering improves overall visual and sequential consistency, as we move from threshold 0.0 to 0.8 with the best performance at 0.8. This suggests that removing semantic outliers helps produce smoother and more coherent multi-scene sequences. However, it may reduce textual fidelity, since some diverse samples are discarded. On the bottom, we show ablations on the training schedule. While supervised fine-tuning alone already produces strong results, adding a pre-training phase boosts performance further, particularly in visual quality and imaging quality. This demonstrates the importance of initializing the model with longer multi-scene structure awareness, which helps the generator handle complex temporal compositions better during fine-tuning. Next, we present 3 qualitative comparisons between our method and state-of-the-art baselines. This is case 1. And here is case 2. Finally, case 3. Across all these examples, our method consistently captures the essence of the prompts and delivers the most visually coherent results. In addition to fixed count scene generation, our model also supports auto-regressive scene extension. Here we showcase several qualitative examples where a new scene is generated based on the preceding scenes as context. Now let's wrap up with a quick summary and a look ahead at future directions. In this work, we proposed Mask²DiT, a dual mask framework that enables controllable and coherent multi-scene video generation. We tackled two key challenges. First, we enabled the generation of a fixed number of visually consistent scenes in a single pass. Second, we extended this framework with auto-regressive scene extension, allowing the model to generate additional scenes conditioned on earlier ones. And finally, we designed a mixed training strategy that combines both modes of generation. As for future directions, we plan to generalize the model to real-world and in the wild videos, handle variable length scenes with dynamic prompts, extend the total video durations, support diverse video resolutions, and further improve motion dynamics and realism.